for attending in person. I know that there's a lot of conflicting ML events happening, but we're really excited to have Professor Phil Schneider from The Ohio State University visiting to give a seminar. Phil's worked on a lot of things in the past, but these days he's really focused on how to use machine learning for signal processing and inverse problems, especially looking at generative models. And I'm really interested to hear about how we might be able to make them a little bit more reliable for things that I care about. So I'll let you talk about using them for conformal prediction. So thanks so much for coming.
Thanks, John. Thanks for all you guys for attending. I know how busy all of you are. So this is joint work with a couple PhD students of mine and then a colleague who is in biomedical engineering, but he sits in a hospital at Ohio State. He has direct access to MRI scanners and radiologists and stuff. Okay, so I'm going to talk about at a high level imaging inverse problems. So there's some unknown image X we'd like to get access to, but we observe some measurements of it. M is some generic, possibly stochastic operator that masks or distorts or corrupts X with noise. And there's a lot of different incarnations of how this appears, like denoising, deblurring, in-painting, super resolution, phase retrieval, computed tomography, magnetic resonance imaging. All these things are examples of this problem. I'll focus a lot on MRI in this talk, in part because I know John likes MRI, and a lot of this work was funded by an NIH grant on MRI. But so in this context, one of our goals is to recover that image X, get an estimate of X that is somehow pleasing to look at, that is accurate. But we might also want to do something like extract quantitative information about it. So for example, maybe at the end of the day, we're interested in diagnosing a pathology, whether pathology is present or absent in X. And the way things are going, maybe we can do that with artificial intelligence. And so maybe at the end of our processing chain, there's going to be some classifier. And maybe that's what we really care about. The image we get in the middle may be interesting to humans, but may not be ultimately the most useful thing. So those are a couple of the goals we can imagine. And there's all sorts of other quantitative information that exists in different applications that you might want to extract from that image X.
We do a ton of inverse problems there.
Awesome.
Yeah.
So these inverse problems are challenging because number one, they're often ill-posed, meaning you simply don't get access to full information about X from those measurements Y. So MRI is a great example where you collect a small fraction of the samples that Nyquist theorem tells you should collect to get full information on X. And there's another kind of recent issue is that as methods to solve these inverse problems have gotten more powerful, they've gotten to the point where they can hallucinate in a bad way, meaning they give you an image that actually looks really great, but there's some aspects about it which are just fundamentally wrong in terms of they don't match the ground truth. And so again, in medical imaging, if we're trying to make a diagnosis and we get this image recovery that has like imaging features that are simply not present in the ground truth, we could make the wrong diagnosis. So those are some of the challenges. And just to show you some examples visually of this ill-posedness, in the top we have an in-painting problem, or this is the true image we don't have access to. These are the measurements we do have access to. You could say our goal might be to recover that true image. But in this case, you can sort of just see intuitively that there's really no way you can do that because there's so many possibilities of what that face could be. So here are just some examples that we happen to generate these with a generative method, but as you can tell, they all look like decent examples of what that true image could be, but they're all quite different from the true image. And then here's another example where this is an MNIST digit, and we see a very noise corrupted version of it, and so we want to recover that digit. And these are some plausible hypotheses that you can see are all quite different from the truth, but they're all equally, plausible given the knowledge we observe, which is these measurements Y. And here's some examples from the FAST MRI paper that shows some hallucinations. This is the true MRI brain image, and you can see that the reconstruction looks really nice, except for the fact that it has this strange visual artifact here. And here's another one with the brain where you can see it inserted this strange line here. And so those things, could give you the wrong diagnosis in potentially. So these are some of the things we're struggling with in these inverse problems. And so when we recover this estimate x hat of our image, we would like to really know how precise that is. Is it accurate? Is it inaccurate? What is the uncertainty that we face? And so, for example, one of the things we could do is if we knew that it was really inaccurate, we might just say, look, I'm going to start over and collect new measurements because I really can't use those. Especially important in safety critical applications like medical imaging. But what's typically done in most of the literature these days regarding uncertainty quantification for images is there's methods that produce uncertainty maps like this, this is a zoomed in image, like a zoomed in version. This is the ground truth image, which is the brain. This is a zoomed in version of the true image. And then these are uncertainty maps. There's different ways to compute them, but one way to think about it is if you look at all the different plausible hypotheses of what that image could be, and then you look at the variance across those hypotheses, you can make images that look like this. And these uncertainty maps, when you look closely, what they really do is they just sort of indicate more or less where the brightness is in the original image, because where it's brighter, where the pixel values are larger, that's where you're going to make a larger error in estimating them. Where the image is very dark, it's very easy to tell that it was dark, and you're not going to make much error. So we would posit that these kind of ways of looking at image uncertainty are not really all that useful in practice. And if you show these things to radiologists, they don't really know exactly what to do with them. They're not really willing to spend their time looking at these. They just don't really know how to deal with that kind of uncertainty information. So
they're just eyeballing it, right?
Yeah, it's like they really do want to know, like, is the image that I've reconstructed, is this diagnostically relevant or not? But if you show them an image like this, they have a hard time answering that question based on that information. So
I have a question about the comment you made about the signal intensity.
Yeah.
So if I use like coefficient of variation where I normalize by the mean, would that solve the problem?
That would be an interesting thing to do. We haven't done that, but I think you would get different looking images. And once again, I'm not sure that a radiologist would look at that and say, oh yeah, that's what I want to see. Like where the mean is close to zero, you would get a massive, expansion. Like, I don't know if it would give you useful images, but I guess another issue with these is these are based on pixel-wise statistics. So you're just looking at the variance in each pixel, and that's not really going to show you when there's uncertainty across pixels. Yeah. Another issue with these. Okay, so so in this talk, I have 4 different sections, and I don't have to go through them all. I can chop off some of the later ones, but the first 2 are sort of about how we're trying to deal with this issue of coming up with reliable ways to interpret the accuracy of an image. And then the second half of the talk, or last 2 methods, are sections of the talk are different posterior sampling methods that we've developed as part of that process. So let's just start with the first one. And so so let's say we have some generic image recovery method. This could be a simple method. It could be a complicated method. We'll just call it R. And what it does is it takes the measurement and it gives you some image estimate. And these 0 subscripts are used to indicate test quantities versus calibration quantities, and that will become evident soon. And what we'd like to know is the accuracy of this image estimate relative to the truth. And I put accuracy in quotes because there's a lot of different ways to really think about accuracy and how you define it. So in our work, we just use an arbitrary image quality metric of this form, which is some function that takes the approximation and the truth and gives you a scalar output. And we're going to call that scalar Z0. And we can think of Z0 as, in some cases, when Z0 is higher, that's good. So like if the metric is measuring PSNR or SSIM, then you want Z0 to be high. But there's a lot of other metrics, like these are some neural network sort of perceptual quality based metrics, LPIPS and DISCs, where a better score is lower. So for most of these slides, just to pick one, I'll choose the higher preferred metrics. But the key point is that in practice, because we don't know the ground truth X naught, we don't know Z naught. Z naught is what we would like to know, but we don't know it. And so our whole objective is to somehow estimate Z naught. But we'd like to come up with some sort of guarantees on Z naught. So rather than giving you a point estimate of Z naught, we're trying to give you a bound on it. And if we're talking about a higher preferred metric, we want to come up with a lower bound. So we'll call that lower bound beta. And now this is going to be a probabilistic lower bound, or at least that's what we're seeking. And now I'm going to use uppercase variables to denote random quantities. So what I'd like is to find some beta naught such that the probability of this image accuracy being greater than this lower bound, given the observed measurements, is greater than 1 minus alpha. And alpha is some small chosen error rate. Maybe it's 1%, 5%, something like that. And so now, if I can do this, then I've given you a beta naught, which is really sort of a lower bound on how good this image is. And it could be a lower bound on any of these metrics or other ones as well. So that's sort of one of the ways we've taken a viewpoint on this problem, giving something that is more useful than these pixelized error maps. So then the question is, okay, how do we do this? So let's talk about sort of an impractical bound motivated from just sort of statistics. And we'll start assuming that we have a perfect posterior sampler. So this is some sort of possibly sophisticated neural network approach. And what it does is it gives us C different image samples. And these are images that are plausible images given our measurements. So this would be the posterior distribution of images given measurements. And the samples we're generating, if they're perfect, are very similar to the true sample in the sense that these are all IID realizations of this distribution. Now this distribution, this posterior, is something we don't have access to. It's this massive object. So this is really just sort of imagining what if we could do this. So if we could do this, then the next thing we could do is we could plug those perfect posterior samples into our image quality metric, and we could get some image accuracy samples. And so all these samples would have tildes on them. And so the thing about these image accuracy samples is that, like the true one, they're all IID samples of this posterior here. And so if this is the case, in order to construct a bound of this form here, where we want this beta naught that is a lower bound on the true unknown Z naught, given our measurements, we can actually do this by just generating an infinite number of these perfect posterior samples, and then computing the empirical quantile of this error rate alpha. And the reason we can do this is that there's some theory that says if these the set of samples converges in distribution to this random variable, then these empirical quantiles converge to the true quantile, and this beta is just the true quantile of this random variable. So basically, this is something we would love to do. We can't do it because we can't generate an infinite number of samples and because we don't have a perfect posterior sampler. But it sort of gives us an architecture that we could say, this is sort of what we would like to do. So maybe we can go ahead and do an approximate version of this and then fix it with something called conformal prediction. So that's sort of the high level. This is sort of the motivation that is guiding the approach or the way that we use conformal prediction.
You guys have a question?
Yeah, so sorry, going back to the first. So
Yes.
Z naught and Y naught are sample part coupled, right? I mean, Z naught is the original sample that's generated from Y naught, but other tildes are all independent samples.
X now that's generated from one.
Sorry.
Yeah. So there's this conditional distribution, which fundamentally we simply don't know what X naught is, right? Or Z naught. Both of these guys are just one possibility, one sample of this distribution, this posterior distribution.
Okay, what I mean is, then there is some underlying model, presumably, which took X naught and did a deterministic translation of that to get Y naught. That's the connection between X naught
kind of a
and Y naught.
stochastic, because usually there's noise involved. If it was deterministic, then this posterior would collapse to it.
Let's say it's just a projection, okay, for a deterministic projection. Then I start with an X naught. This is not your algorithm, just behind the scenes. And then projected it down to get Y naught. But then X0 tilde is independent because it's a sampler. But X0, I'm trying to understand the difference between X sub 0 and X sub 0 tilde.
Yeah, so X sub 0 is the ground truth, which we don't know. And this ground truth is really just one sample from this posterior distribution. And it's, in that sense, it's no different than any other sample from the distribution.
Maybe he's asking why is x tilde 0, 1 independent from x 0?
Oh, because we've assumed that we are generating these conditionally on y, we're generating them independently. Usually you draw some like code vector, you put it through some methodology. And so we're just saying, suppose we can do this. Because part of our assumption, we can draw independent samples. Okay, is that sort of making sense?
Sort of, maybe we can chat later.
Yeah, okay. So this is kind of the high level. And
Wait, I have a question about your question. You're kind of saying like, is this a frequentist view or not, right? Like, are we making an assumption that it's a deterministic input?
So
versus a
I think it
distribution
comes
right?
down to Adam's question as well, what I'm asking. So that's,
Okay, like if y is just x plus Gaussian noise or something,
it could be.
right, then we're saying x0 would be the mean. Like, how is x0 also a sample?
X0, so there's some true X0,
Yeah,
and then you add noise to it to get Y. And now, when you ask, what can I infer about X0 from Y? You can't say exactly what it is. It's a distribution, right? And so now the true sample is just one sample from that distribution of this posterior distribution.
yeah, like it's on the support, but then if I'm gonna draw a bunch of samples. Are you saying that x0, I'm enforcing that I do draw x0 and then I have x0 tilde 1 through c is other samples?
So the ones that I'm creating, which the ones I suppose I have access to are these ones.
Mhm.
This one, I don't know.
You're saying it exists there?
Yeah, it exists.
And I could have sampled it, but
I could have sampled it,
Okay.
right? Statistically, they're all the same. But practically, these ones, I'm assuming I can generate, and this one is the object of this whole investigation. Yeah. Okay. So that's kind of like what's guiding us. Now in practice, we have imperfect posterior samples from some black box method, and we have a finite number of them. And so we would like to come up with a valid lower bound, and we're going to use something called conformal prediction. And what conformal prediction does, is sort of secret sauce, is that we need to have n calibration samples. So in this case, the calibration samples would be copies of true images X and their corresponding measurements Y. And these are in addition to the test measurements that we have. And there's also a true test X naught, but we don't know it. So these are the things we do know. And the way that this conformal prediction works is just like on the previous page, you compute those empirical quantiles. But now I'm putting a hat on them because these are also, this is an estimated lower bound that's going to be imperfect on this. This is the thing I would like to construct. These are just empirical estimates of it. So that's similar to what I'm doing over here. But I'm going to generate a different estimate for each one of my calibration samples, as well as from my measurements. So that's why I is going from the test sample to all the calibration samples. And then maybe I don't need to get into the details, but there's sort of this specific method. You compute these bound violation scores, you compute another empirical quantile. And finally, what you get is you take this rough bound and you adjust it, you calibrate it using some quantity you compute with a calibration set. And this new bound satisfies this so-called marginal coverage guarantee, which is on the left. This gives us the lower bound that we want. And on the right, this says that our lower bound is actually pretty tight. The larger the calibration set, the closer the lower bound to the upper bound. So n is the number of calibration samples. So as I get more calibration samples, I can sort of hone in on this probability. Now, this probability is a little bit different in the sense that this probability is looking over random calibration sets and random test samples. So it does not hold for a specific calibration set. So it is something that we have to be aware of. But the bound does hold as long as these bound violation scores are statistically exchangeable, which means that this is a weaker condition than IID. It means that I can take this set of random variables and I can shuffle it, and statistically, its joint distribution is the same. So they could be correlated, but you just have to be able to shuffle them and have that correlation still manifest. So this is sort of the overall procedure. And if I show this as a diagram, maybe it makes a little bit more sense. So here's this true image. I don't know, so it's sort of grayed out. And there's some image quality or accuracy metric that I use my recovered image. And there's some true accuracy, which again, I don't know. It's grayed out. But what I'm doing is I'm constructing a bound. I'm using these posterior samples as almost like surrogates of the true image. I'm computing that metric for each one of those posterior samples. And I'm computing this approximate bound for the test sample here. And then I'm using this calibration set, which I've collected to use conformal prediction to get this conformal bound. And at the end of the day, we know that here's the truth, here's my lower bound. We know that the truth is somewhere in that lower bound with an accuracy or a probability of at least 1 minus alpha. So, so it gives us a sort of confidence that this lower bound is valid. And as you shrink the error rate alpha, as you make that smaller and smaller, your bound gets looser and looser. So you have to sort of, you get to choose alpha, but if you choose alpha too small, maybe your bounds are too loose. So it's sort of a design choice.
Yeah, just a quick question about the previous slide.
Sure.
The last formula, is that a condition? So my understanding of conformal inference is that it's a guarantee over random samples of X and Y. So the conditional on Y not is I'm a little bit confused by that.
Yeah, so that's right. So we're thinking of, so this is my measurement, which I'm thinking of as a random vector. So this is a joint probability over sort of 3 sets of randomness. It's V and the calibration set conditional on the measurements. So you have sort of, it thinks about these calibration sets as random. So it's sort of like, imagine that you do this experiment over and over again with a different calibration set. And now you look over many, many Monte Carlo trials, which I'll show you. And then you can see these bounds really are manifest.
And all those replicates. Why not is how fixed.
No, so in that case, the Y naught is actually changing. So yeah, so this is sort of, yeah, these are both random in this case.
Is that a random probability that you get there?
Oh, yeah, that's a good point.
I think maybe there shouldn't be a conditional on why not. If I
Yeah, why not equal to little why not? Is that what you mean? Or
Yeah.
yeah, you either fix it or
Yeah, that's a good point.
well, we can, yeah, we can.
Yeah, I think maybe yeah, it should be gone. Okay. So okay, so this is the overall procedure here. I'll show you some examples if we apply this to MRI with the fast MRI knee data. And here we're looking at 4 different metrics, so PSNR, SSIM, LPIPS, and DIST. And we're showing a scatter plot of the true quality on the x-axis. This is the thing you would like to know. And this is the bound. And so each one of those points shows the true quality in the bound we compute. And this is the line that's just x equals y line. And so you can see that whenever the bound holds, the blue samples are to the right of the red line, and whenever the bound fails, the blue samples are to the left. And roughly speaking, if we choose an error rate of 5%, then you'll see that 5% of the samples are on the wrong side of the line. And so what we did is just to verify this, we did 10,000 Monte Carlo trials, where in each trial we took a random test and calibration split of the data set. We did the calibration procedure and then we tested on the test samples. And averaging over those trials, if we have a target coverage of 95%, the empirical coverage you can see it's definitely meets our target. It's just a little bit worse, and we expect it to be a little bit worse because of this useless here. So that's sort of just an illustration. And one of the important things is you can see there is a pretty good adaptivity or correlation. As the true image quality increases, the bounds also increase. So it's doing a pretty good job of predicting them. Yes.
What is DIS?
Oh, yeah. So DISC and LPIPS are some sort of modern perceptual quality metrics.
Is it like a deep learning based one? 'Cause it
Yeah,
looks
both of these are deep learning. Sorry, both of them are deep learning based, and both of them sort of involve an ImageNet backbone architecture, where you look at feature maps at different depths within an architecture, and you compare those feature maps between the true and the estimated image, and you look at sort of the statistics, how close the statistics match. And it sort of mimics what happens in the human visual cortex, which is also doing sort of a similar multi-stage thing, computing different feature maps, as you get through the different visual layers. And so it ends up giving you qualities that seem to match closer to what people perceive as visual quality, metrics that are close to visual quality. Yeah. And in particular, this one there's a study of about 50 different metrics in MRI with radiologists, and they correlated how the metrics behaved versus what the radiologist thought was good quality. And this was the one that was the winner for MRI, according to that study at least. So that's one of the reasons we look at it.
So each point here is a different why not sample?
Yeah.
So some of them are just easier to reconstruct than
Exactly.
others.
Yeah. Yeah, there are some outliers. Yeah, they're just difficult samples. Or yeah. Okay, okay, and so one of the ways that we can use this is through a multi-round acquisition procedure. So what we do is we start out being very aggressive. And so in MRI, when we say R equals 16, acceleration 16, that means we take 1/16 of Nyquist. And what we do is we compute our conformal prediction of the image quality. I think in this experiment, we used discs, and we said, let's come up with some sort of threshold on discs. If the image quality is better than our threshold, we stop. We say 16, R equals 16 was good enough. If not, we collect a few more vertical lines in MRI, and now we have R equals 8, and we repeat this process, and we stop as soon as the quality is good enough according to our conformal prediction. And the way that we set up that quality threshold is we calibrate it so that when we're in an acceleration of 2, which is in MRI, that's collecting quite a bit of samples, that the empirical coverage, according to this conformal procedure, was essentially like 5% error. And we showed now that if you do this multi-round procedure where, okay, R equals 16 is too rough, you don't accept any of those images, but at R equals 8, we end up accepting about 60%, R equals 4, 35%, and so on. And when you average across the acceleration rates, you go from 2 to about 5.4. And importantly, when you look at the samples that were finally accepted, their empirical coverage is very close to the target. There is a slight modification that we can do to this where we would get exactly the target, but we didn't do that in the study. So this is just showing like one way you can use image quality bounds productively to actually speed up the acquisition process.
Question.
Sure.
But so every time though, you're just adding a random sample?
So we, you mean how
the random acquisition measurement?
Yeah, there's you could do it any way you want. We use a particular sampling pattern called GROW, G-R-O, that my colleague developed a few years ago, which is a deterministic pattern that competes with like the best random designs. But it's also deterministic, so we know exactly which ones to add to kind of complement the previous ones.
Okay, but if you didn't care about computation, you could use this setting to also find the best choice as well, right?
That could be complicated because we did have to calibrate at each one of these accelerations with those particular sampling patterns. So I think that becomes more challenging. There might be a way around it, but yeah. Okay.
This is like for one patient.
Yeah, one patient's in the scanner. So you collect a few lines, you construct the image, and then you evaluate, is this good enough? And then if no, you just immediately collect a few more lines. So this whole procedure here would take.
But what's the ground truth?
Oh,
So
yeah.
Data max is something that someone tells you like, I'm comfortable with this error.
Yeah, so we had to just set that.
Okay.
And for this, we set it at the level that you would get with R equals 2 if you did one round. And we're saying like, how much can I beat that by if I use multi-round?
But how do you compute like the error? Like what's the ground truth of these?
Oh, we don't, yeah, that's the whole reason we have developed this conformal methodology is because we don't have the ground truth. So we're giving you a lower bound, or in this case, an upper bound on disks that holds with, 95%. Yeah, all of this is motivated by the fact that we do not know the ground truth. If we knew the ground truth, it would be trivial.
So beta max is something that I learned from a different.
Oh, beta max is just something I set. It's like a target threshold. And so we just chose it just for this experiment, such that it would equate to what you would get at R equals 2 sampling 95% of the time. So that was just something we chose for the purpose of this experiment. And then we said, let's use that threshold, but sometimes you can get that at R equals 8. Sometimes you can get it at R equals 4. You don't, no.
Hello, could I ask a question over Zoom?
Yeah.
Hi, coming from the laptop, sorry. This is
Oh, sorry.
Yami, and hi.
Yeah, we can hear you.
Yeah, we can hear
Okay,
you.
great. Yeah, I had a question about the computation. So if I understood the procedure properly, every time you want to compute this bound, you need to like generate many posterior samples. And so like, is it possible to like do this while the patient is on the table, or am I misunderstanding that part?
Yeah, so it kind of all depends on how many you need to compute and how expensive they are to compute. So I'll show you in a few slides that for slightly different application, we can get away with 2 posterior samples.
Cool.
And now, okay, if you're using a diffusion method, that could still take you a while to generate 2 samples. But for these studies, we actually use the conditional normalizing flow, or you could use a GAN, and that can do it just with 1 neural function evaluation. So it would be pretty quick.
Cool. Thanks.
Maybe like a quarter of a second.
Makes sense. Thanks.
Okay, great. So yeah, so that's, I think that's, oh yeah, so then another question that you might ask is that this whole procedure, all of this validity is kind of based on this idea of exchangeability of the scores, the test and calibration scores. And so the reviewers are always critical of this, and they're always like, yeah, but in practice, there's going to be a distribution shift. We did a little study with the MRI, the fast MRI knee, and with the fast MRI knee data, it comes in volumes, and the volumes are slices of the knee from front to back. And so the study we did is we calibrated on the center slices only, but then we tested on different slices from edge to center. And so here it shows you the slice location, what happens. So 0 would be the center image, and so if you test and calibrate at 0, you get exactly the coverage, which in this case was 90% that we were looking for. Now, as you start to go away from the center slice further and further, you can see that the empirical coverage, does go down. For some metrics, PSNR and SSIM seem to be pretty robust. Actually, it stays about the same for the first 3 or 4 slices, but then eventually it goes down too. So, but yeah, so our methodology so far is only valid, if we have this exchangeability. But there is some recent theoretical results that show that there's sort of a path to going forward. That if your calibration sets, if let's say your test sample is your test distribution is a certain distance from your calibration distribution, for example, measured in total variation, then it's possible to just use a more conservative error rate alpha and still guarantee that coverage. So there's sort of a path forward. We haven't done a lot of work in this direction. We've done some simulations, but yeah, this is work to be done. Okay. So so let me present sort of another take on this, which is more of a task-based or quantitative version of this, which is to say, let's say the objective is not to reconstruct the whole image, but to somehow extract some quantitative information. So as an example, you want to know whether this patient has a meniscus tear or not. So what's natural to do is to train a binary classifier, assuming that you have a bunch of clean images with labels, tear, no tear. And so you can train this binary classifier on these clean images. But if you think about it, if you apply that classifier to reconstructed images, it's probably not going to work the way you expect because those reconstructed images look a bit different than the clean ones. And so it'd be a bit dangerous if you just apply that classifier to the reconstructed images. And so what we want to do really is we want to estimate the classifier output on the unknown true image which we don't have access to, but we want to do it through access to our accelerated measurements. So here again, the Z, the thing we're trying to estimate, is now not an image quality, but it's like, in this case, it's some real number that might be the probability that our soft binary classifier sets. So if the classifier thinks it's like 90% chance that there's a tear, it's going to output 0.9. And we are trying to extract that number 0.9 from the measurements Y. Okay, so in this case, what we're going to do is rather than just lower bounding it, we're going to construct upper and lower bounds. And we want to guarantee that the true probability or the true task output is within this prediction interval, up to a certain error rate, or with probably at least 1 minus alpha. So again, this is sort of how the flow looks like in a picture. There's this true image, we don't know. There's the task, there's a true image output, we don't know. What we do know are measurements Y. These measurements, we put them through our approximate posterior sample, we get some image samples. We put those through the task, we get some task samples. We use some calibration set to calibrate those samples, and finally we get a prediction interval that is guaranteed to hold the unknown true task output with some probability 1 minus alpha.
So Z0 is a probability, or like could be.
It's a number in this meniscus tear application. It's a probability that this classifier thinks.
Do you get useful upper bounds in that interval, or you should just get a lower bound? Because if the number's pretty confident, it should probably spit out something large.
Yeah, so I mean, you could formulate it any way you want, but we we thought it's more natural to get upper and lower bounds, just because it's we want to know, like, it's a choice. We could have done a one-sided bound too.
That's what I'm asking is, do you end up getting like the upper bound being less than 1?
Yeah, definitely.
So you would reject if it spit out super confident.
We chose to, yeah. I mean, it really depends on the classifier. We've found that with the number of samples in fast MRI plus, we can't really get a very confident classifier. It's sort of, maybe it maxed out at 0.9. It can never be more confident than that. Once it's calibrated, the classifier is sort of calibrated on its own so that the probabilities that it generates are actually meaningful. And those probabilities, they never get to 1. But maybe in some other application they could. So here, just diving into a few more details, like there's different options for constructing those prediction sets. One approach would use the empirical mean of your posterior sample. Another could also use the posterior variance. And there's a fancier approach that uses quantile. In all these cases, at the end of the day, you're going to get an interval, lower, upper, down. And you can think of the width or the length of that interval as sort of a measure of uncertainty. And so, like, the tighter that interval, the more certain you are about your whole imaging pipeline. And so this is just some visualizations of the MRI knee. So this is a knee image. And the meniscus tear is really what's happening in a really tiny region of the image here. And when you look at what's in there, it's this is the ground truth. And the reconstructions you get at R equals 16, they vary quite a bit from the ground truth. At R equals 4, they're a lot more similar. You can kind of appreciate the challenge of detecting meniscus tear from this image. So there is definitely quite a bit of uncertainty there. And so now let's take a look at some of these different methods. So in terms of the width of the interval, that could be an indication of how powerful this method is. So you can see that the AR method, which is the simplest one, gives you the widest interval. And as you use more sophisticated methods, the interval size shrinks. And so, like, we're giving you more precise estimates of what that classifier believes. And then you can also look at the number of samples that the mean interval versus number of posterior samples are generated. And you can see with the CQR method, it seems like with 2 samples, you already get pretty good interval length. Yes, you can improve with more, but maybe in the interest of computation, you would just stick with 2. And we can also do the multi-round procedure here. But instead of looking at, lower bound on quality, now we would look at the interval length and we want to make sure we're getting tight intervals, and we would stop this multi-round task as soon as we had a tight enough interval. And so here again, we sort of calibrated things so that one of the methods, the simplest method, gave R equals 2, 1% coverage. And then with these more sophisticated methods, you can get up to R equals 5 or 6 with the same coverage. So, yeah, so that's it. So I do have a couple more sections of the talk, but maybe in the interest of time, I think time is almost up. So,
Are people able to stay at all interested, or should we? No, you can take another 5 minutes.
okay, I can talk a little bit more about a diffusion method that we've developed. So I know how familiar you guys are all with diffusion, but let me just very briefly.
Familiar. Right, everyone's like very familiar with diffusion.
Okay, so
Yeah.
I don't need, I can skip this. So one of the things I want to point out with diffusion in inverse problem, or diffusion in general, it is based, on in the reverse process using the score function. But importantly, the score function can be related to a conditional mean or MMSE denoiser through Tweedy's rule. And it's just an affine transform. And we find that this denoiser is often a lot more intuitive to think about rather than the score itself. And when you go to solving inverse problems with diffusion, that denoiser goes from something that looks like this to something that includes the measurements Y and the conditioning. And so when you look at all the different diffusion methods that have been proposed for inverse problems, essentially they boil down to come up with different approximations for this conditional score or conditional denoiser. They're all just variations on it. And so when you start to look at the details, so you can always, even if you have a score-based method, using Tweedy's rule, you can kind of convert it back to a denoiser output, and then you can visualize it. And you can also compute the mean square error on that output, because you know that the exact denoiser minimizes MSE. So MSE is actually like a valid criteria for how sophisticated or how well is this diffusion method working different points of the reverse process. So here's on the left, we have a super resolution example. On the right, we have an in-pain example. And each column is a different method. The number shows how many total NFVs is used for the method over its entire reverse process. And in the first row, we're showing what is this denoiser output at 25% of its NFVs, at 50, and at 75%. And as expected, things get better. But you can see that what happens here, especially early on, is that the images that are being generated, or the denoiser outputs or score functions, are actually pretty bad. There's some massive artifacts. They're really pretty bad approximations of the thing that the methodology says we should be plugging this in every iteration, but we're really plugging in something very different. So we thought this was an opportunity for us to maybe try to do a better job of estimating this and therefore improve the overall reverse process. So that's sort of what we set out to do. And the methodology we're advocating is what we call fast iterative renoising. And the renoising is maybe what's sort of novel about this. And so more or less, it goes like this. So we are going to iterate 4 steps, possibly multiple times, 4 iterations, multiple times per diffusion step. We're going to start by initializing at the information that we get from DDPM or DDIM. We're going to do a denoising step. And then we're going to do one of these proc steps. And if you look at these first 2 steps, this is exactly what diffPIR does, which is one of the methods. But one of the things we're doing differently is when we denoise, we're actually going to try to figure out how much noise is in the denoiser output. And there's different ways to do this. But you can sort of train a method to give you a pretty decent estimate of the average variance in that denoiser output. We're actually going to use that in this proc step. What diffPIR does that uses just sort of a surrogate. It doesn't try to get it exactly. It just uses a rough guess. But the part that's sort of a novel contribution is when you look at the error coming out of this proc step, it is very non-white. It's very colored. And the diffusion denoiser was trained on white noise. If you simply plug this estimate back into your diffusion denoiser, it doesn't work well. Especially like an in-painting, that denoiser could give you, very different results in the masked and unmasked pixels. And if you plug that back in, the proc step does, if you plug that back in, the denoiser will kind of persist with these strange artifacts. So what we said is, okay, let's add in some colored Gaussian noise into this X hat that sort of equates the noise, makes it white. And once we have that, we can put it back into our denoiser and denoise again. And so at every diffusion step that we run, we actually run several iterations of this. Every iteration, we set the target noise level so that it decreases. We start out with a lot and then we gradually bring it down. And here's just one example. This is at the very first diffusion step, t equals 1000. If we run 50 iterations of this method, we get really good outputs just from this alone. So this is, you could say, it's a kind of like plug and play method. It's actually not really using diffusion, but it is introducing some noise. So it's something we haven't seen before, but it's sort of a template that we can use. Now, in terms of how we compute that noise, so if you had an SVD, you could compute this noise spectrum exactly. If you don't have an SVD, we came up with an approximation based only on the forward operator and its adjoint, and this seems to work pretty well, good enough. So this is sort of just how we compute this, this particular conditional mean. And now you need to plug this into a diffusion reverse process. But because this fire itself uses several NFVs, if you just plug this into DDPM, you'd be using thousands of NFVs. So we're gonna have to subsample the diffusion process. We're gonna use DDIM, and we're gonna have to we subsample it, and then for each one of these subsampled reverse diffusion steps, we run a few iterations of this fire algorithm. So now the question is, how many do you run? So we use a water filling sort of approach to determine this. The water filling procedure works. It's easy to explain if you think not about variance, but the inverse variances or precisions. So here is what you would get for DDPM, if this is for FFHQ. If you look at across the DDPM steps, the precision starts out super low, variance super large, and it gradually increases the precision as it goes to step 0. And we're going to subsample that with DDIM in a particular way. And then when we run fire, that's what these green lines show. It shows at this step, we run one fire iteration, we get up to this precision, another one, this precision, and so on. And the way that we're budgeting these steps is we have some overall targets, and we want to make sure that at the end of our fire runs, we surpass this target. And so that's essentially how we figure out how many iterations to run for each diffusion step. And so using this overall procedure, we want to try to compete with state-of-the-art methods over a range of different NFV budgets, let's say 20, 100, 1,000. And let me just show you a table. So this is, so for example, if we're going to compete against 1,000, with 1,000 NFVs, DPS is one of the best methods, so we compared against that. If we're looking at 100 NFVs, we looked at PyGDM and diffPIR. And if we're at 20, we're looking at DRM and diffPIR. These are sort of the best in-class methods. And we looked over a range of different inverse problems and 3 different metrics. And if you look, we're sort of winning across the board of 1,000, 100. And at 20, there's a couple places where we're in second place. But overall, 33 out of 36 cases, this method is winning. So that's the main idea. If we have a linear inverse problem, if we have a nonlinear inverse problem, something like phase retrieval, we have an extension of this method that uses expectation propagation to iterate back and forth between our linear fire and a scalar MMSE inference stage, passes sort of messages back and forth. And essentially, we just do one of these message passing iterations per fire iteration, and applying this to phase retrieval, we're getting state-of-the-art performance relative to plug-and-play methods as well as diffusion methods. So, yeah, so thanks for listening. I don't want to keep you any longer.
Thanks.
Any other questions?
On the previous project, why did the conformalized quantile method work so much better than the other ones? Like, yeah, then.
So the way that I think about it is that you could say that these estimates here are like rough estimates of the lower and upper bound. And the closer those rough estimates are to kind of the nature of the bound itself, the tighter, better things will work. And so the bound itself, you can kind of argue is looking at some sort of quantile of some random variable. And this is trying to get you that based on the information you have. So there's sort of a natural fit between the true boundary quantities. If you had all the information you wanted, it would just be some sort of quantile of some random variable. And this is like getting you very close to that. When you use like, these are sort of more heuristic approaches, intuitive approaches, and they're not really set up the same way. And so there's sort of a gap in terms of their performance. That's the way I think about it.
All right. Thanks, everyone.
All right, thanks again.
Thank you, Phil.